Containers and virtual machines both provide computing services, but they differ in how they achieve virtualization. Virtualization is a process of creating virtual versions of system resources like RAM, CPU, disk, networking, and so on, allowing them to represent multiple resources. Now, a virtual machine is a digital copy of a physical machine, complete with its own guest operating system, system files, and libraries. VMs offer a high degree of isolation, but they can be resource intensive due to the duplication of the operating system, amongst other things. Containers, on the other hand, virtualize at the operating system level or above, sharing the host operating system kernel. They package code and dependencies into standard units of software, enabling applications to run consistently across different computing environments. Containers are lightweight and efficient, as they do not require a separate operating system instance for each container. In this video, the AWS Elastic Container Service, ECS, is discussed as a platform for deploying and managing containers. This video also demonstrates how to build and deploy a complete ECS architecture, including a multi-tier application to provide you with the practical skills of working on AWS. Join me in this mini project. Hello and welcome to my channel. My name is Rajesh and I am a senior solutions architect and a cloud computing trainer with over 20 years of experience in the IT industry. I've spent the last 10 years working on the AWS platform, and I've worked as a solutions architect for clients across the US, UK, and in India. I now deliver corporate training programs for a wide range of organizations, and I'm also the author of the AWS Certified Cloud Practitioner Exam Guide, published by Pack Publishing and available on Amazon and major bookstores. That's enough about me. Let's get on with this video. So this video is all about a mini project that I'm going to walk you through implementing using the AWS ECS platform so that you can get some hands-on experience on deploying containers in the cloud. The agenda for this particular mini project is as follows. We'll start off with a brief introduction to virtualization and containerization. We'll then look at Docker images and Docker anatomy. Now, we're not going to do too much of a deep dive here because I want to stay focused on ECS, but I'm going to give you some overview anyway. We're then going to move on to the introduction of ECS, the Elastic Container Services, and we'll talk about the ECS launch types, the server-based approach and the serverless approach. Next, we're going to talk about Richard Roast, which is a coffee shop business that has chains of coffee shops across the UK, and they're looking to actually embark onto the cloud and deploy their application using ECS. That's where you're going to come in. We're going to take a look at an architecture design plan together, and you're going to have the opportunity to deploy a fully fledged application using ECS and associate services to build a complete solution on the AWS platform. Before we get started, I have one humble request. Please hit that like and subscribe button, and of course the bell icon, so that you can get notified of more mini projects that come in the future. Let's move on and talk about the actual application. So this is a really simple application. It's been designed for Richard Roast, which, as I explained earlier, is a coffee shop business that has a chain of coffee shops across the UK. Now, one of the things Richard Roast like to do is engage with their customers. And to that end, they have a beverage of the month where they would like to provide that beverage of the month as a result of some feedback from their customers. Okay, and essentially the way how they do this is get their customers to do a bit of a poll, and the customers choose from a selection of drinks that they would like to see in the following month, and the one that gets the top vote is the one that's provided in the following month as the beverage of the month. Fairly simple idea. But this is a multi-tier application because it's got a front-end UI, so all of the HTML stuff, some JavaScript, all the wonderful images to entice the customer, and a great marketing strategy to use in order to ensure that they maintain that brand loyalty and brand awareness. That all happens, and that's all available in the front-end UI. In addition to that, they've got a custom form that engages with the customer and gets the customer to provide their name, email address, choice of drink that they would like to see in the following month as the beverage of the month. And the good thing about this is that they're collecting email addresses, so obviously it's good for marketing and their future marketing campaigns. This website is going to connect to a backend database, and that's where the whole multi-tier element comes to it. So we have a backend database that we're going to be also setting up as part of this overall mini project. You will have the opportunity to configure both front-end elements and backend elements, and will give you a good hands-on experience in building this Elastic Container Service solution. Now, obviously, if we're connecting to the backend database, there will be some CRUD operations that can be performed as a result of that, specifically the ability to create entries in the database with the name, email address, and choice of drink selection. So hopefully that's all really clear. Now, the source code for this application, along with all of its necessary bits and pieces like, the HTML file, CSS style sheets, images, all that wonderful stuff, is available to you in our GitHub repository, the link of which is down below in the description of this video. You want to download all of the source code, keep it handy on your desktop, and then you will be able to build out this application as we progress along with this training program. Next, let's go ahead and do some introductions first in terms of technology. I want to do a little overview on virtualization versus containerization, and then we can start moving on from there. Let's do that next. Okay, so let's do a quick recap on virtualization next. Now, virtualization has been around for n number of years. Okay, the likes of Hyper-V and VMware have been cornerstone to virtualization technologies, and without them, perhaps cloud computing might have taken a different shape or form. The fact remains that virtualization allows us to have n number of virtual servers running on the same physical hardware, and this makes better utilization of very, very sophisticated and powerful hardware resources. The way how it works is very simple. You've got your host machine, the actual physical hardware that will have the CPU, the storage, the memory, the processing power needed, and perhaps innumerable fans to keep it all cool, right? And that physical host is upon which we will run our virtual machines. Now, in order to enable that to happen, we need something called a hypervisor. The AWS have their own lightweight hypervisor system called the Nitro system. And with that, we're able to have virtual machines on their platform, which is the EC2 service that AWS offers. Now, virtual machines are essentially virtual versions of physical machines. They have absolutely everything a physical machine would have in terms of its own guest operating system, necessary systems and runtime environments to support your application, and then obviously finally the application. And this could perhaps be for my development environment. Bear in mind that this virtual machine is going to consume some portion of that CPU, of perhaps some local storage, and definitely some amount of that memory. And so you are limited to the number of virtual machines you can potentially have on a host hardware, depending on the resources available on that host hardware. Nevertheless, you can have lots of virtual machines running on that same physical hardware. So I can have my testing environment, I can have my production environment, and I can have perhaps other environments for experimental efforts. Probably not the best way of doing things. Perhaps you want your production environment on a different host altogether, but you get the idea. One thing that I would like to draw your attention to over here is that all these 4 environments are using the same guest operating system. They're all using the Amazon Linux operating system in this example. And that is likely to be the case in most use case scenarios, right? You're using the same stable version of the operating system, probably the latest version of the operating system, all patched and all secured with the latest critical updates. But you do notice that it takes up a substantial portion of your virtual machine. That's a good amount of storage, CPU utilization, memory that those guest operating systems are going to consume anyway. The other reason for having these different environments is because perhaps you might be having different versions of your services, your utilities, and your runtime environments as you work with your application lifecycle. So the production version of your application lifecycle is running on an older, stable version of Node and MySQL in this example, whereas you're building a newer version of your application to make sure that it runs on the latest version of Node and MySQL, to ensure that when those versions get deprecated and no longer supported, you're able to easily transition your application to those newer versions. And so virtual machines have the benefit of the fact that they allow you to run applications in isolation on the same physical hardware because it uses its own guest operating system, runtime, and libraries. So that is one of the primary use cases for having virtual machines. You are able to ensure that these machines are not in any way interfering with each other, causing any kind of conflict. So each virtual machine will have its own guest operating system, allocated memory, disk space, and CPU capabilities, but it also means that you have an extended amount of overhead in terms of managing your virtual machines. You've got to make sure that your guest operating system and even the applications and services and runtime environments are regularly updated, patched, and all of the necessary security protocols and security measures put in place. In this example, we've got 4 virtual machines, but if you had 200 or even 2,000, you need to make sure that all of your different virtual machines were fully patched, fully secured, all of the critical updates applied, maybe even antivirus software if you're using Windows. You get the idea. The point is that this adds to the day-to-day administration of your services. And ultimately, there's a lot of duplication and wasted resources when it comes to virtualization. So virtualization is actually a breakthrough technology because back in the old days, remember, we used to have physical servers. We would have separate servers that ran a single application. When virtualization came along, this all was possible. Amazing. But we can do much better than that. And that's where containerization comes in. And let's talk about that next. And so let's take a look at the case for containers. Now, containers are very similar to virtual machines insofar as you can run multiple containers on the same physical hardware. So we're still utilizing that hardware for running multiple containers or applications that run within those containers. However, the architecture is somewhat different. So with a virtual machine, you had the host operating system, you had the hypervisor, and then you had virtual machines, each of which had their own guest operating system. That changes in the case of containers. With containers, you still have the host hardware. You need the underlying hardware with the CPU, the storage, the memory, the cooling fans to keep everything nice and cool, and all that stuff. But on top of that, we have the host operating system. So the host operating system could be running a Windows environment or a Linux environment or whatever the operating system needs to be. And then on top of this, you've got something called the container engine. And a good example of a container engine is the Docker container engine. So in this scenario, what we have is we have a Docker container engine that is going to help you create and manage your containers. And the best thing about containers is that unlike virtual machines, which have their own guest operating systems each, these containers are going to make use of the host operating systems. They are in fact going to be running as isolated processes on that host operating system. And so when it comes to deploying your containers, we have a much smaller footprint in terms of resource utilization to run your applications. A container comprises of the application, all of the necessary runtime libraries, the services, the utilities that it will need in order to function in isolation on its own. So if you've got a Node.js application, it's got all of the bits and pieces that it needs to run, and it's going to run as a single isolated process on that hardware, sharing that host operating systems with other containers for your different applications or indeed different environments. And so ultimately, you're using far less resources you're running on that particular piece of host hardware in that environment, which means you can run many more containers. Okay, and therefore you are able to utilize your hardware resources far more efficiently, be far more sustainable for the environment. These containers are going to share the host OS kernel. They're going to run as isolated single processes with their own file systems, child processes, libraries, and any applications that you wish to run on them. They're going to be lightweight versus VMs, okay, which means they're also going to start much quicker. So imagine booting up a VM versus running a container task. You're going to find that your containers come up far more quicker. And remember that containers are also portable. So wherever you've got your container engine, you can just move your containers across and put them across to different hardware far more easily than you can with VMs in terms of time, in terms of necessary resources, and perhaps any sort of dependencies that you might also have. So hopefully we're beginning to see the case for containers, and hopefully we can see that containers are far better than using VMs. Another aspect that I want to quickly mention over here is that containers make it possible for you to run microservices and cloud native applications far more efficiently and far more easily than running virtual machines. Right, now that we've seen the key differences between virtualization and containers, how exactly are containers created? Let's take a look at that next. So containers are created from something called a container image, for example, a Docker image. How a Docker image is created? Well, we start with something called a Docker file, which is a manifest that describes the various components of that image. That is then used to build the image. And then once you've built the image, you can go ahead and launch and run your container from that image. Fairly simple. In terms of the Docker file, then let's take a look at how this manifest, this file looks like. Now, if we take a closer look at this particular file, this Docker file, you can see that there are several commands that are being run in it. And these commands basically are instructions on how to build that image. More importantly, every command that is being run to create or do something new is essentially creating something called a layer in your image. So this first command over here is where we are actually creating a base image from something called a parent image. Okay, and usually this involves downloading a pre-configured parent image. It could be the application component of an operating system, or in this case, we're trying to set up PHP and the Apache service. But we always start with some form of base image, what we call the parent image. Then we're running the next command where we're adding the extensions to MySQL, and that becomes layer 2. And so that adds yet another layer to your image. We're doing some updates. That becomes the third layer in the image. And hopefully you're beginning to see what's happening here, that every command that is being run adds yet another layer to this image. Each of these layers and the image itself comprises of an entire file system, where each layer acts as a differential element that goes on top of the overall image. So we've got the next command, which is to copy some code into the HTML directory. That's our layer 4 in this example. And ultimately, that's how you end up building the image. Each of these layers are what we call intermediate layers, differential layers that stack one on top of the other. And it's interesting to note also that layers that change more often, the commands or the components of your image that are going to change more often, should really be higher up the stack. And the reason for this is that Docker uses something called layer caching. Now, I'll not go too much in depth into all of that because that's obviously more for a Docker course. But ultimately, what you need to be aware of is that Docker makes use of layer caching in order to speed up the entire process, because there's no need to recreate your layers if they haven't changed. And this speeds up the process of creating new images as you do variations. So for instance, in this example, if we make a change to the actual code that's going to be running our application, then that should come much later on in the actual list of commands, higher up the stack, so that you do not recreate the entire thing all over again, and you allow the system to use previous cached images. Once you've got all of your different components, all of your different commands that you've run and built out your image, you get your final image. Now, this is your Docker image, and this needs to be placed into a repository, which we'll talk about shortly. But ultimately, this is what you use to launch your containers. This final image has got the entire file system. It's got all of the different components, all of the applications, the runtime, the dependencies, any environmental variables, all that it needs to run as an isolated process on your server. Now, once you actually deploy your container, another key aspect to bear in mind is that obviously these layers and the final image gets deployed to create your container, but every container also has its own read-write layer. Remember that these layers are all read-only layers, okay? But every container will also have an additional layer, that's the read-write layer. And so all changes that you make to a running container, such as writing new files, modifying existing files, deleting files, are all written to this very thin read-write layer. Now, if you want to learn a little bit more about how these layers actually interact with each other, then you need to understand a little bit more about the storage driver, and you can get more information at docs.docker.com/storage/storage driver. So feel free to have a read of that to get a better understanding about these layering systems. Now that we've understood how these Docker images and container images are created, let's go ahead and talk about the Amazon Elastic Container Services that makes use of these images to launch your containers. Now that we have a base understanding about containers and Docker files and Docker images, let's move on and talk about the Amazon Elastic Container Service. Now, the Amazon Elastic Container Service enables you to orchestrate and run highly secure, reliable, and scalable containers on the AWS platform. And you can use the ECS service both as a managed service from AWS using what's called the Fargate launch type, or where if you need to manage your own containers and the underlying host machines, the EC2 instances, then you can go for the EC2 launch type. We'll start off with a brief introduction and overview of both of these types, and then we'll move on to actually discuss how you go and deploy a multi-tier application using the ECS service. Let's continue where we left off. Now, to really understand the Amazon ECS service, first we need to discuss its components. When you're working with ECS, you're still going to have to build a container image. And in order to build that container image, you're going to use a Docker file. This Docker file will then help you to architect your container image or your Docker image, which needs to then be placed in a repository. Now, you could place your Docker image in any one of two repositories. In fact, you can even have third-party repositories as well, but the most common ones to use are Docker Hub, which is a container repository built for developers and open source contributors, and you can share your container images with the general public. So Docker Hub is obviously a hub that's maintained and managed by Docker, and you can create those public repositories or even private repositories for your teams and your enterprise. In addition to Docker Hub, you can also use the Amazon ECR service or the Amazon Elastic Container Registry service. Now, this is just like Docker Hub. It provides a place for you to create repositories within which you can store your container images. The best thing about ECR is that it integrates seamlessly well with other AWS services like IAM roles and KMS for encryption services, etc. Now, once you've got your container image in its repository, we can start using the various ECS components to deploy your containers. And the first component that you're going to work with is something called a task definition. A task definition is basically a blueprint for your application. It's another text file in JSON format that describes the parameters of one or more containers to form your application. It will contain several parameters such as the image that you're going to be using. So the image that you've saved in the repository, what image are you going to be using to launch your containers? The IAM roles that it will need in order to interact with any of the services, and the IAM roles that your task are going to be using for that container application. Next, you're going to have a container definition, and a container definition is used to describe the different containers that are launched as part of the task. A task is essentially an instantiation of your task definition when you run that definition as a task, which is basically the container. So the task is the container. Other components of your task definition include things like the networking mode, okay, whether you're going to use a specific VPC, for instance, the number of containers that you're going to be deploying, the CPU and memory that you're going to use for your containers within a task, the storage volumes that you may want to use and consume as part of your application, and the ports that you're going to be exposing. So for instance, are you going to be using HTTP, HTTPS, or another proprietary port to connect to your application? Once you've defined your task definition, you can go ahead and actually deploy your task. So you essentially run your tasks to launch your containers. Now, before you actually do that, you also have to create something called an ECS cluster. So an ECS cluster is just a logical grouping of your tasks or services, a logical grouping of your containers, if you will, that run on infrastructure on the AWS platform. So this ECS cluster is where you actually define things like the VPC and the subnets and other parameters that will allow you to group together your containers. And within the ECS cluster is where you're going to deploy your ECS containers in one of two launch types. You'll have either the EC2 launch type, which is where EC2 instances are launched, and within these EC2 instances, your actual containers are deployed. Okay, so when you run a task, what will happen is the task run process will deploy the containers within the EC2 instances that you've designated as part of that cluster. The other type of launch type you would use is the serverless launch type, which is what we call AWS Fargate, and we'll discuss that in an upcoming slide. You can also create something called an ECS service. Now, an ECS service can be thought of as the auto-scaling service for Elastic Container Services. So in the same way as you have auto-scaling groups for EC2 instances so that you can scale out and scale in your instances, in that same manner, you have ECS service, which manages the scalability of your actual tasks. If a particular task fails, then ECS service will take care of replacing that failed task. And likewise, you can maintain a set number of ECS tasks running at all times, or you can adopt a scaling policy like target tracking or step scaling to scale out and scale back in. So the ECS service allows you to specify the number of tasks to run. You can use the ECS service scheduler for scheduling strategy, and you can also use it to define your task placement strategy. Now, task placement strategy, a little bit more advanced for this particular module, but it allows you to define the way how your tasks are placed in order to either reduce the number of instances that you consume, what we call bin pack, or spread them across multiple availability zones, or use a random placement strategy. There's a couple of other services that I want to quickly talk to you about before we move on to the next slide. So we've got ECS service that enables you to deploy ECS containers on external platforms such as your on-premises services, and you must provide the necessary access to that on-premise location to manage your ECS cluster. You'll also need to install the ECS agents on those instances. And then we've got something called the AWS Copilot, which is a command line interface that simplifies the building, releasing, and operating of production-ready containerized applications on Amazon ECS from a local development environment. So next, I want to dive deep into the two launch types that we have on ECS, the EC2 launch type and the Fargate launch type. We'll start with the EC2 launch type next. So we'll start off by taking a look at the EC2 launch type. Now, the EC2 launch type is basically where you have your ECS cluster, where AWS will deploy EC2 instances that will have the ECS agent installed on them. And on those EC2 instances, your containers will be deployed. When it comes to the EC2 launch type, therefore, you've got to bear in mind that you are managing those EC2 instances. You've got to make sure that they're patched and updated, and that adds to the administrative overhead element that you must take into account. Let's take a look at how you would go about deploying ECS using the EC2 launch type. So obviously, first, you will still have your container registry that will house your container images. Okay, whether that's Docker Hub or ECR, the choice is yours. You'll need to set up a VPC, a virtual private cloud, within which you will build your network, your private network that will host those EC2 instances. In order to ensure that you follow best practices and you think about things like high availability, you want to make use of multiple availability zones within your VPC and ensure that you deploy the appropriate number of subnets comprised of both public and private subnets to ensure that, again, you're thinking about high availability as well as access to the internet. You'll configure your ECS cluster and you will define exactly which subnets within that VPC you're going to be using to host those EC2 instances that are running the container agent. You'll also set up an auto-scaling group, and you will use that auto-scaling group to define the deployment of those instances that will be as part of that overall cluster. The ECS auto-scaling group scales your EC2 instances using the auto-scaling group capacity provider, and based on your requirements, you will be deploying the necessary EC2 instances to scale out or scale back in, depending on your specific needs. Next, you obviously still have to go ahead and set up your task definition. Now, your task definition is going to actually dictate exactly how your containers are deployed. And you can also make use of the ECS service that enable you to define the number of tasks that will be deployed and provide auto-scaling features for the tasks specifically. So you've got the auto-scaling group that looks after the auto-scaling of the actual instances, but then remember that the ECS service is providing the auto-scaling element for your actual tasks. Now, when it comes to the ECS service, you can define a number of different scaling policies. You've got target tracking scaling policy or step scaling policy. You can define the parameters that will trigger the scaling activity based on things like CPU utilization, memory utilization, and the application load balancer request count per target metrics in order to trigger the necessary scaling actions. To define the scaling, you would set the target percentage, what's called the target capacity, for the utilization of the instances, and you can use target tracking scaling policy to scale out and scale back in. Now, once your service is all set up, your service will then run tasks, and those tasks will be deploying containers within the EC2 instances in your EC2 launch type configuration. Couple of additional points to note then with regards to this particular launch type is that with the EC2 launch type, these are ideal for large consistent workloads. You can use the EC2 reserve instance pricing model or even the spot instance pricing model in this regard, and therefore you can benefit from those discounts that come with that offering. Also bear in mind that on-demand EC2 instances will be chargeable while you have your containers in a running state. And so you want to think about the overall cost element and your cost strategies depending on the type of workloads that you're running on the ECS platform. Okay, so that covers the EC2 launch type. Let's go ahead and talk about the Fargate launch type next. Okay, so next I want to take a look at Fargate. Now with Fargate, we've got the same setup. We need a container registry to house our container images. We still need our VPC and we need our cluster, and also we want to make use of multiple availability zones so that we offer high availability. However, the architecture is really different when it comes to actually managing your cluster. In fact, you don't have to manage any of the EC2 instances because AWS takes care of that for you. So here's how it works. You've got your task definition, which calls that specific image, that Docker image. You've got all of the other parameters defined in the task definition to set up your containers. You make use of services, especially when you want to deploy multiple containers within an auto-scaling service for your tasks to ensure that you can scale your tasks. That obviously then triggers your actual tasks, but your tasks will actually launch the containers in a AWS shared Fargate environment. Okay, so it's a shared services environment where your tasks will get launched that AWS has access to. You do not have direct access to this environment, but your containers will reside in that shared environment amongst other containers that perhaps belong to other customers. Nevertheless, your containers are completely isolated and secure, so you need not worry about any kind of conflict there or any kind of issues with other customers getting access to your containers. That does not happen. Okay, so your containers are obviously deployed in a shared services that's outside of control. How do you actually access your application? Well, what happens is AWS injects ENIs into your VPC that is directly connected to those containers. And over private IP, you are able to access the application running on those containers. And so in essence, when you set up your load balancing configuration, so your application load balancer that's going to be used to distribute traffic to your various containers, you're going to be using IP addresses as the targets in the target group in your application load balancer configuration. And we'll take a look at how that works when we get on into the demonstration. A few points to highlight over here then is that each task is isolated and does not share the underlying kernel, CPU, or memory with another task. You have access to a shared pool of resources. Your tasks are run in this shared infrastructure via ENIs from your VPC. Load balancing uses IP addresses to set up targets. So as I mentioned, we'll take a look at this in the actual lab. You're charged only for the containers you use. You are not charged for the EC2 instances that are running your containers. So that's pretty awesome, right? And they are ideal for smaller workloads. Nevertheless, a lot more cleaner, a lot more less management overhead on your part because AWS takes care of all of the patching, the updates, and all the stuff that needs to go in with regards to managing EC2 instances that run your containers. Okay, so that covers both the EC2 launch type and the Fargate launch type. Let's get on to something really interesting now. Let's actually take a look at the architecture reference diagram of the application that you're going to be deploying in the lab. Let's do that next. Now that we've covered all of the theory around ECS, ECR, Docker, and all of its various components, it's time to move on and actually get some hands-on practical experience. Next, we're going to take a look at an architecture reference diagram that we're going to use to deploy Ritual Roast Coffee web application. Remember the application that they're going to use to engage further with their customers by allowing their customers to poll for the beverage of the month. That application needs to be deployed on the ECS platform. And I'm going to walk you through the different steps and the different components that's going to be used to build out this application. Hopefully you will then develop the necessary practical experience to feel confidence in deploying real-world solutions with your customers and your clients. Right, so let's go through this architecture diagram. So obviously we're going to be working on the AWS platform. Now the first thing you want to do is build out a VPC, because your compute services and including your database services are all going to be hosted within a VPC architecture. And for the purposes of best practice, you want to be working in at least a minimum of 2 availability zones, if not 3. Within these availability zones, within the VPC, you're going to be building out subnets for your VPC. We're going to split them up by having some public subnets and some private subnets. Okay. Public subnets are going to host only those services that need to be exposed out to the internet. The rest, the database, the compute services, all of that stuff is all going to be in the private subnet. Next, we'll need to make sure that your VPC has access to the internet, because obviously we want to access those services from the internet. Our customers will be coming from the internet to access that website. In addition to that, we'll also be deploying some NAT gateways. Now, the purpose of the NAT gateway is to allow the instances or the services that run in the private subnet, such as the compute services, such as the application, any kind of access that they might need to the internet. If you were deploying EC2 instances, for instance, that needed access to the internet to download updates, patches, etc., you'd need a NAT gateway in this regard. You'll also be deploying databases, and we'll place the database in the database subnet. So you want to separate out your databases from your compute services, obviously, so that there is separation. And although in the real world you'll be deploying a multi-AZ architecture, if you were deploying RDS in order to offer high availability and failover elements, we will just be deploying the one instance for the purposes of this exercise. But in the real world, you definitely want to be thinking about multi-AZ and even read replicas depending on your business use case. Next, we're going to be deploying an application load balancer. Remember, the application load balancer is going to be used to distribute traffic that comes from the internet to our containers, okay, because we're going to have multiple containers for the purposes of high availability. So we're going to be using an application load balancer for that purpose. We'll also be setting up an ECS cluster. Within the cluster, obviously, we'll be deploying our containers. Now, this particular mini project is going to be focusing on the Fargate launch type. So we're going to be thinking about serverless. You don't have to manage any EC2 instances that host those containers. We want AWS to take care of that management overhead for us. And in terms of the additional components that you will need for this application, one component is going to be AWS Secrets Manager. So you may be wondering, what's the requirement for AWS Secrets Manager here? You got to remember that your containers are running the application that will need access to the backend database, in this case MySQL. Now, we will be setting up MySQL with a standard authentication mechanism of a username and password. You do not want to be hard coding those credentials in the application code. You want the application to dynamically retrieve those credentials from Secrets Manager, and hence the reason for having Secrets Manager in this architecture. In addition to that, you will need to set up some necessary roles. Specifically, you'll also need to set up a task execution role, and the task execution role will grant the application and the containers access to the various services that are being built and deployed within this architecture. So for instance, the ability to actually talk to Secrets Manager, you need permissions for that. That's all going to be in the task execution role. In addition to that, we'll be setting up some environmental variables so that we can tell the application running on the containers where exactly are the various services and components that it needs. So for instance, what is the secret name in Secrets Manager to access the secret credential? So that's a reason. The environmental variables may also have, for instance, the endpoint address for the MySQL database. So you'll need some environmental variables to be configured. In addition to that, obviously we want to deploy our containers, right? So you're going to need to set up your container image, and for that you'll need a Docker file. Now, I'll be supplying you with a Docker file available in our GitHub repository, so at least you don't have to worry about trying to build out that one, but feel free to modify it if you need to. And you can use that Docker file that's available in our GitHub repo. You'll be using that Docker file to build out the Docker image, and you'll also set up a repository on Amazon ECR so that you can host that image in ECR. So I'll walk you through that process as well. Once you've got all of the necessary bits and pieces in place, all the ingredients to this recipe, if you will, you're then going to build out your task definition. That's going to be the critical element of your ECS deployment. Your task definition is going to identify which image we're going to use, details of the secrets manager, the task execution role that you're going to incorporate, and all the other stuff we spoke about in the earlier slides. Once you've configured your task definition, you will use that to then deploy a service, an ECS service. Remember, an ECS service is effectively an auto-scaling element for your tasks, for your containers. You will define certain key parameters within the service, which will be used to trigger and launch your tasks. And because we're using the Fargate launch type, the tasks will deploy containers within the shared services platform that AWS will manage entirely for you. So the containers will be deployed in AWS Fargate, not in your VPC. However, access to those containers will be injected into your app subnets. So we will configure the settings so that the ENIs are deployed in your app subnets so that you can access those containers. And your users from the internet will be able to access your containers and the application that runs on them. Okay, so that's the overall architecture, and you can see that there are a number of moving parts to this entire solution. Now we're going to jump on into the AWS Management Console, and you're going to be able to build out each of these components individually so that you can get the much hands-on experience you need in order to understand how this solution is constructed. Okay, so let's go ahead and do the interesting stuff next. Okay, so step one is going to be where you're going to create a VPC. Now, a VPC is a private network that you build within your AWS account in order to house all of the resources that belong to a specific project. Now, you could use more than one VPCs, but ultimately you need a VPC in order to host resources like EC2 instances and databases, as well as ECS containers. So that's the first thing you need to do. You need to build out a VPC, ideally in accordance with best practices, which means you want to make sure that you segregate your different subnets between your public and your private environments of the VPC. And you should be deploying your solution across multiple availability zones to take into account for the necessary configuration for high availability. So this is what we're going to be building. We're going to build a VPC, and we're going to make use of 2 availability zones. And within those availability zones, we're going to deploy 6 subnets, 2 of which are going to be part of the public subnets. So that we've got 1 in availability zone A and 1 in B, 2 app subnets, which are private subnets, and 2 database subnets, which are also private subnets. Now, within the public subnets, we will be deploying a NAT gateway, and this is to facilitate any internet requests that our applications might have from the private subnet. Obviously, we'll need an internet gateway. And in addition to that, we'll also need to ensure that we allocate some security groups. Now, security groups allow you to define the sort of traffic that you're going to allow inbound to your applications. So we're going to need a security group to accept inbound traffic to the application load balancer, which is going to be used to distribute traffic to our containers. The application load balancer will accept traffic from the internet, and therefore will need to look for requests on port 80. Then we will be also creating an app security group that is going to be associated with our containers that will accept inbound traffic, again on port 80, because it's all HTTP traffic, from the application load balancer. So any resource associated with the application load balancer, which in this case will obviously be the application load balancer itself. And then we have a database security group, which will accept traffic only from the containers, so from any resource associated with the app security group on a specific port. In this case, we're deploying an RDS database, a MySQL database specifically. So the port that the database security group will be looking for is 3306. And any traffic on 3306 will be passed on to the RDS instance that you will later deploy in this mini project. Okay, so that's the basic architecture. Let's jump on into the AWS Management Console and build out this VPC. Okay, so here we are in my AWS Management Console. This is a development account, and you want to make sure that you're operating in the North Virginia region. Now you want to search for VPCs from the search bar and just open that up in another browser tab, and that will take us to the VPC Management Console or the VPC dashboard. So there are 2 ways to set up your VPC. You can follow the manual approach, which allows you to really understand how all the various bits and pieces work. I've done that in one of my previous videos, but in today's session, what I want to do is I actually want to go and use the wizard, simply because we want to spend more time focusing on the ECS build out. But it's just as easy. So if you click on create a VPC, you've got the manual method where you would click VPC only. But if you want the help with the wizard, then you just select VPC and more. And this is a preview of what your VPC is going to look like. Now we're going to be making changes to this one shortly. So the first thing that I want to do is, obviously I want to choose the actual subnets and the availability zones that my VPC operates in. So for that, let's just scroll down for a second. So we want to spread our workloads across 2 availability zones. So we've got 2 selected by default, so we can leave that as it is. You could change the different availability zones that you want to use, but I'm happy with US East 1A and US East 1B. We need 2 public subnets for our VPC as per the previous slide, and we need 4 private subnets. 2 for the app layer, which will contain our containers, or in the case of Fargate, we'll have our ENIs so that we can access our containers, and then 2 for the database layer. I also want to customize the CIDR block range. So if we scroll a little bit above, you'll see that my VPC CIDR block range, the default CIDR block is 10.0.0.0/16. That's fine. We can keep it at that. But I want to change the actual CIDR blocks for the individual subnets. Okay. And normally it would select different blocks with sufficient number of IP addresses away from each other so that you can build multiple blocks for that particular type of subnet. So public subnets, for instance, it starts at 10.0.0.0/20. Now 20 gives you 4,000 odd IP addresses. We don't need that many. Let's change that to 24. Even that's quite a lot really for this exercise, but we leave it at a default value, standard /24 IP range. And also I'll change the 3rd octet there because I would prefer to use it starting with .1.0/24. Another public subnet this will be .2 and again /24. And essentially what we're doing here is we're just customizing the size of our subnets, okay? And our public subnets will be consecutive. So public subnet 1 will be 10.0.1.0, public subnet 2, 10.0.2.0. If we had a public subnet 3, we could call that 10.0.3.0. And each of these individual blocks are separate from each other, okay? They do not overlap, and that's important. Your subnets cannot overlap, otherwise it just won't work, and in fact the system won't let you do it that way. Then we're coming to our private subnets. Now in our private subnets, you want to leave a bit of a gap, because in the real world we may only start off with 2 public subnets, but we may need another 3, 4, 5, 6 public subnets. And so if you leave a gap, then the consecutive order of a particular category of subnets isn't broken, and that just is considered best practice. So the default value given by AWS is 128. I think that's a bit too far off for our corporation, Ritual Roast. Let's start off at 10, and again I'll just put this as 24. So if that's 10, then this can be 11/24. Those are 2 app subnets, and then we have our database subnets. We'll start our database subnets at 20, again /24. Again, this is just an example. You can streamline this much further. Okay, so then that one can be 21, and let's put /24 in there as well. Okay, so we've got 6 subnets. We are going to make use of a NAT gateway. Now in the diagram, the previous diagram where we were looking at the architecture, we had 1 NAT gateway per availability zone. For the purposes of this exercise, I'm only going to use 1 single NAT gateway for the entire VPC, only because NAT gateways do cost you a bit of money. If you run this project for just a couple of hours just to test it all out and stuff, it might just be less than a 10 cents even. But if you let your NAT gateway run for the entire month, you may incur a few dollars. So you want to make sure that once you've done this mini project and you're satisfied with the outcome, that you terminate your resources at the end of the project. Okay, so we're going to go with 1 NAT gateway in 1 AZ. Endpoints allow you to access resources within the AWS ecosystem without using NAT gateways. For the purposes of this lab, we're not going to do any, so we'll just say none. And you want to make sure that these 2 tick boxes are also checked. Okay, so this is your architecture as it comes out. Now, in terms of the naming conventions, like I mentioned, I like to change this just so that it's a little bit more intuitive. So I'm going to untick this auto generate box, and I'm going to give my VPC a name. So I'm going to call this one Ritual Roast VPC, and then the public subnet in US East 1A, I'm going to call this one Ritual Roast public subnet 1 US East 1A. So I know exactly where it is, right? And likewise, I can name the B public subnet 2, and that will be 1B. Okay, private subnet. Now this private subnet is going to be for the app layer. So we're going to call this one Virtualization app subnet US East 1A, and we'll call this app subnet 1. And again, the same thing we'll do down here. So that's the app subnet 2. So that's my second subnet, US East 1B. Okay, then we need our data subnet. So Virtualization data subnet 1 US East 1A, and the same thing, data subnet 2 US East 1B. So this is where we've just named our subnets. You've got two public subnets, one in 1A and one in 1B, two app subnets that's going to contain our containers, 1A and 1B, two data subnets that's going to contain our database. Now the route tables is where you define exactly how traffic flows within your subnets, between subnets, and out to the internet. So we need to provide a name for the public route table. Okay, so the public route table, I'm just going to call this one RR public RT. Okay, RR public RT. We only have one public route table, and you will notice in the actual highlighted boxes that it starts off at Richer Roast, and there are two subnets, the public subnet 1 and public subnet 2, that are connected to the public route table, and ultimately that connects out to the internet gateways. And I'm going to call this one RRIGW. So the RRIGW stands for Richer Roast Internet Gateway. So essentially what's happening is any resources in these two public subnets will make use of the public route table, within which there's information on how to connect to the internet using the IGW, the Internet Gateway. Now, we've got the app subnets, so let's do that next. So the app subnet 1 requires a route table of its own. So this is RR app subnet 1 route table, okay? And then you've got the same thing over here, so you can see the highlighted boxes. This is for the app subnet 2, okay? So we're going to call this one RR app subnet 2 route table, okay? Then you have the database route tables. So the database route tables also, in this case, the databases don't need to access the internet, but if you had any other resources that needed access to the internet, they too could be connected to the NAT gateway in order to send internet bound traffic. So we'll call this one RR data subnet 1 route table, and likewise the final one RR data subnet 2 route table. Now each of these four route tables are connected to the NAT gateway. So this is the NAT gateway over here. So we'll need to give the NAT gateway a name. I'll call this one RRNAT, and that is as simple as that. So hopefully this naming convention is a little bit more intuitive. Okay, I know which ones are my public subnet, which ones are my app subnets, and which ones are my data subnets, and I can tell which route table is associated with which subnet, and within those route tables, internet bound traffic is connecting to which resource. So obviously the public route table is sending internet bound traffic via the internet gateway, whereas the app and the data route tables is sending internet bound traffic via the NAT gateway. Okay, so we've got this architecture built out. Obviously, if you were to have, two NAT gateways or one NAT gateway per AZ, this architecture will get a little bit more complex, but that is obviously best practice, because the idea is that if one of your AZs goes down, if there's a availability zone outage and you happen to have your NAT gateway in there, you obviously want to back up another NAT gateway in another availability zone to support traffic. But this is just a lab. This is just a mini project in a safe environment. So hopefully we don't need to do that. Okay, so let's just go ahead and just make sure that everything is fine. So I've got my IP address block for my VPC. I'm using 2 availability zones, 2 public subnets, 4 private subnets. I've customized the IP addressing. I've got 1 NAT gateway, no endpoints. Everything else is fine, and I can click Create VPC. And AWS is going to go through and run and build out the entire VPC architecture for you. And this obviously is a lot quicker than doing it manually, but I highly recommend that you look at one of my other videos and manually build out your VPCs if you have a chance, because it will give you a good understanding about how VPC connectivity and traffic routing is meant to be designed and built out. Just be aware that the NAT gateway requires an elastic IP address, and so when you do terminate your NAT gateway, don't forget to release the elastic IP address. Cool, awesome. And that's our VPC built, so we can go ahead and view the VPC now. And this is the VPC resource map that you can look at. So we've got our Richard Roast VPC, public subnets, app subnets, data subnets, and we're all looking good. So our data subnets points to data subnet route tables, app subnets point to the app subnet route tables, okay? And it's easier to then identify which resource belongs to which route table, etc., and therefore which endpoint in order to access the internet. Okay, so if we just take a look at a couple of other things, if we go to route tables, and you've got a list of the route tables there, so you can see that they're all listed. If I take a look at the public route table and I look at routes, you will see in fact that there is a route to the internet, okay, which uses the internet gateway. So I know that's going to work just fine. Likewise, my app subnets, okay, there should be a route to the internet via the NAT gateway. So that configuration looks good. Go down to the NAT gateway and we can see that the NAT gateway is also properly configured. It's got a public IP address. Okay, it also resides in public subnet 1. So the NAT gateway has been placed in public subnet 1, which is where it needs to be in order to send traffic to the internet via the internet gateway. The NAT gateway acts as a relay, a network address translation service for our resources in the private subnet. Okay, so the next thing that we need to do is build out security groups. Remember, there are 3 security groups we need to build as per the previous slide. So we'll start off with the first one. So the first security group is the application load balancer security group. So we'll call this RRALB SG for security group. Okay, make sure you place it in the right VPC. So that's the Richard Roast VPC. And then I'm going to add an inbound rule. So we're going to accept traffic on port 80 or HTTP. And the source of that traffic is going to be the entire internet. Okay, so what happens is we're allowing individuals on the internet to access our load balancer so that they can get connected to our Richard Roast web application. And I'll go ahead and click create security group. Okay, I need to give it a description. We'll just put the same thing in there and click create security group. Okay, so that's our Richard Roast ALB security group. Let's go back to security groups. And I'll just quickly put this name in here as well, just so that it's easy to identify. Create another security group. Let's call this one the Richard Roast App SG for application security group. Now remember what I said earlier. This security group is going to be associated with our containers, and it's going to allow traffic on port 80, but only from resources that belong to the application load balancer security group. So only the application load balancer security group can send traffic to our containers. And obviously that traffic would have originated from end users out on the internet. So we're going to go down and click Richard Roast there to choose the right VPC, create an inbound rule, and I want HTTP, and I want it to come from load balancer, application load balancer security group. That's where the traffic is going to come from. And click create security group. And so that's my app security group. Okay. And then let's do the final one, which is the database security groups. So RR data SG. Okay, choose the right VPC, add the inbound rule. And this time, obviously, we're connecting to a database, MySQL database specifically. So we want traffic to port 3306 to come from the application security group or any resource associated with the application security group, which will be our containers. So you want to select that one, and then you want to click create security group. Go down to security group there. You can actually tag these names in the tag section as well. I'm just copying and pasting it in the name column there. Okay, so you can actually set the tags up as you create your security groups as well. Okay, so pretty much our VPC is done. We've built out our subnets, we've built out our route tables, NAT gateway, internet gateway, and we've also done our security groups. That's our VPC set up and configured. Let's move on to step 2. Okay, so step 2 is where we're actually going to go ahead and create a repository in the Elastic Container Registry. Now remember, this is where you're going to be hosting your container images, your Docker images that will be pulled down by the ECS service in order to launch your containers. So we need to first create a repository within which we will build a Docker image and upload that Docker image or that container image to. So let's go ahead and create that repository first in Amazon ECR. Okay, so here we are back on my AWS Management Console, and what I'm going to do is I'm going to search for ECR in the search box here and open that up in another tab. And so here we are, this is the ECS Management Console. Right, okay, so just click on the left-hand side and then you want to click on repositories, and we're going to go ahead and create a repository. And we're going to set up a private repository, which means that you will need to authenticate to it in order to access it. And I'll obviously show you how that's done, but you can also create public repositories if you wish. And we'll call this repository Ritual Roast. Okay, so this is our Ritual Roast repository. And you want to leave everything else as it is. Obviously, you could encrypt it using KMS, but that isn't the purpose of this particular lab exercise, but obviously something to consider for real-world applications. Go ahead and click Create Repository. Okay, and that's your repository created. So Ritual Roast has been successfully created in private registry. Okay, so what you also want to do is make a note of the URI. The URI is the repository location, and so you want to make a note of this because you will be using this URI a little later on in this mini project. So the next step is to actually go ahead and build out a Docker image, which we are going to then upload to this repository. So join me in step 3. Okay, so welcome to step 3. In step 3, I'll show you how to actually build a Docker image. And essentially, in terms of our architecture diagram, what we'll be doing is we're building a Docker image. You will need a Docker file. Now, the Docker file is available to you from our GitHub repository as part of the zip folder that I'll show you in a minute. But you will use that Docker file to basically build your Docker image. And once you've built that Docker image, then we'll move on to actually uploading that into ECR. So next, let's go ahead and build out our Docker image. Now, in order to create your Docker image, you will need to make use of Docker. Okay, so what you could do is you could actually download Docker onto your local machine. So if you're running a Windows or a Mac or a Linux machine, if you just go to docker.com and click on the Get Started link over there, you have installers for Mac Silicon, Mac Intel, Windows, and Linux. If you are using your local machine to interact with the AWS environment, you'll also need to download and install the command line interface. Again, you've got installers for Windows, Mac, and Linux. And then you need to also make sure that you configure the command line interface with an IAM user that has sufficient privileges to interact with your AWS account. So you could create an account in IAM, give that account administrative rights, and then you configure your CLI with those privileges. Now, all of that stuff is available in the documentation, so you can go ahead and do that. I'm actually going to walk you through setting up Docker and using Docker to create your Docker build, your Docker image, using an EC2 instance instead. And the reason for that is some of you out there may be using a work laptop or a work desktop, and you won't have the permissions to install applications like Docker or the CLI on your local machine. And I thought I want to cater for everyone who is watching this mini project. So you can do that as well. Even if you do have a machine that doesn't have any of these restrictions, you can simply deploy a new EC2 instance in your AWS account and use that as your Docker build server. And that's what we're going to do. So what we need to do for that is obviously we'll need to go into the EC2 console. So I'll open that up in another browser tab. Now, one thing to point out is that this build server, this Docker server that's going to be used to build our Docker images, it's going to need some permissions. It's going to need permissions to upload our Docker image from the build server into Amazon ECR, and we need to remotely connect to it. Now, we can remotely connect to it if we deployed that server in a public subnet, and then configured security groups to allow inbound SSH on port 22. I don't want to do that because that's not best practice. Instead, we're going to use Session Manager to connect to our EC2 instance. That will be our Docker server. Now, Session Manager is a really powerful tool, allows you to remotely access your servers on the AWS platform without having to open ports like 22 and 3389 for remote desktop protocols, which is a much more secure method of doing it. So in order to give our EC2 instances these capabilities, the ability to connect to it using Session Manager and the ability for that server to be able to talk to ECR, we need some permissions. And where do we do permissions? You got it right. We do it in IAM roles. So we're going to go into IAM first, and I'm going to create an IAM role. Now, there's a couple of predefined permissions that AWS has already created, what we call managed permissions, that we can use. So we don't have to get too complex here. If we just go into roles, and I'm going to create a new role. Okay, so the trusted entity type is AWS Service, and we're actually going to go with EC2 as our service use case. And specifically, we're going to be setting up some policies for EC2. We're going to give an IAM role to our EC2 instance that we deploy. That's going to be a Docker build server. So we'll click next. So the first one is called Amazon SSM Manage Instance Core. So what this does is it allows you to remotely connect to an instance using Session Manager. Okay, it provides the permissions necessary in order to be able to access the instance using Session Manager. So this is going to be one of them. And then the other policy that I want to attach to this role is EC2 instance profile for image builder ECR container builds. Okay, and this particular policy allows you to basically upload ECR images. So the Docker server, the server that's going to be our Docker build server, once we build the Docker image, if it's got this policy, we can upload that image into ECR. So that's the other one that I want to attach as part of this role. And so I'm going to click next. So we need to give it a name. I'm going to call this one IAM role grant EC2 SSM and ECR access. Okay, hopefully that's really clear exactly what this role does. And then you want to go ahead and click create role. And that's my role created. IAM role grant EC2 SSM and ECR access. And then when we go to launch our instance now, we will attach this role as part of that instance profile. So here we are in our EC2 dashboard. So I'm going to click launch instance. And I'm going to call this one my ritual roast Docker build server. Wow. Okay. Yeah. So that's what we're going to call it. It's going to be an Amazon Linux machine. You want to use the Linux 2023 AMI. Okay. And we're going to go with the T2 micro. That's all you actually need. It does not need a key pair because we're using Session Manager. That's the other beauty of connecting to the instance. You can access it using Session Manager and it doesn't need a key pair. You just need to make sure you put it in the right VPC. So I'm going to put it in the richer roast VPC. And I can put it in a private subnet so that it's nice and secure. So let's put it in app subnet 1. It can run in there as well. That's actually where we're going to run our ECS tasks as well, but they're separate from each other. Because it's in the app subnet, we don't need a public IP address. And in fact, I'll just attach it to the default security group. Because again, it doesn't need you to allow any inbound permissions on port 22 or 80 or any of that. So we just attach it to the default security group. So that's fine. It's basically allowing all traffic to itself. Scroll down a bit. We don't need to make any changes in terms of the storage. If you click on advanced details, you must make sure that the IAM instance profile is the IAM role you just created. Okay, if you don't do this, it's not going to work. Okay, so you want to make sure that the instance profile has this role included in it. Okay, so the IAM role grant the EC2 instance SSM and ECR access. That role is now part of that instance profile. Everything else, leave it as it is. and we'll launch the instance. Okay, this is going to take a couple of minutes to launch, so I'm going to pause the video over here, and once it's up and running, let's just see what it's doing. It's just launching there. Once it's up and running, we'll continue the video. Okay, so here we are with our Ritual Roast Docker build server. If I click on it, that's up and running now, and it's passed the system status check, and I can click the connect button, and you can use Session Manager to connect to it because it's got that IAM role. So that's going to take me into the shell of my Linux box. Okay, and when you log into an Amazon Linux machine, you want to use the local user account in Amazon Linux machines, which is the EC2-user. So we just want to change the user context to EC2-user, and the command for that is simply sudo su minus EC2-user. That's going to put us into the EC2-user context. Okay, and we can see where we are. If we do a pwd present working directory, we're in the home EC2 directory. Fantastic. Okay, so in order to build our Docker image, we are going to have to install Docker on this machine, and before doing that, we should run a update to see if there's any operating system level updates that are required. So the command for that is sudo yum update -y. And great, there's no updates waiting, there's nothing to do, so we can proceed with installing Docker. Sudo yum install Docker. Okay, it's going to ask you for permissions to do that, so say yes to that and let that run through. Takes a few seconds. Okay, so that is completed successfully. I'm just going to clear the screen, and the next step is to actually start the Docker service. Okay, so you do sudo service docker start, and that starts the Docker service. And so the next thing that we need to do is actually give our EC2 user permissions to interact with Docker. So currently, although we have installed Docker, remember we did it with the sudo command, so we elevated our privileges in order to gain access to those commands and in order to install Docker. However, in order for the EC2 user itself to have permissions to work with Docker, we need to give it certain permissions, and we do that by adding it to the member of the Docker group. So you can run this command, sudo user mod -a -g docker EC2-user, and what this does is it places the EC2 user in the Docker group. Okay, now to activate this change, you need to log out and log back in. So I'm just going to exit and then exit again, and that's going to take me back to my list of instances. So I'm just going to click on my instance and connect in again. Okay, now that we've logged back in, once again, just change your account into EC2-user. Okay, and that puts us in the EC2-user account context. Present working directory, yep, I'm in the EC2-user location. Okay, now the next thing that we need to do in order to build our Docker image is to get access to the source code files, which also contains the Docker file that you will use to build the Docker image. And if you go to our GitHub repository, the link of which is down below in the description box, in fact, we have a list of various mini projects that we've done, so feel free to download those and try them out. But the ECS mini project will give you access to the Ritual Roast code zip file. And what you want to do is you want to just make sure that you copy to your clipboard the raw link, okay? Because that's what we're going to use to download the actual zip file. So just right mouse click on raw and click copy link address, and you want to go in and you want to go into your systems manager again, and this time we're going to download that file, that zip file. So the command is wget, and then I'll just paste that link there. So that's my GitHub repository, the raw link. Okay, so that has downloaded, and we can check. So you can see there is the zip file. I'm going to clear the screen, run ls again, and there's my zip file. So we're going to unzip that zip file, and that's going to extract the contents of that zip file. And that's done. Got to clear the screen again, another ls, and there's the actual folder. So if we navigate into that folder, you will see, in fact, that the contents of that folder includes the Docker file, which you will use to build out your Docker image. It's got all the other files relevant to the applications. It's got the index.html file, which is the front end of that website. Fantastic. Okay, so I want to quickly show you what's in the Docker file. So we're just going to do a nano Docker file. And in the Docker file, we have got a simple set of commands. This is really a simple Docker file. Okay, it can get quite complex. Basically, we're starting off with a base image of Apache. We're then running a few commands to install some extensions for MySQL, doing some updates. And finally, we're copying the source code of our website to the var www.html directory. Okay, that's as simple as that. And that builds an image with all of those bits and pieces needed in order to run that web application. So we'll just exit out of this. Okay, so the next thing that we can do is use the docker build command to build our image. Now, before we do that, what I would like you to do is just navigate to the Elastic Container Registry. When we did set up the Elastic Container Registry, remember I had told you to make a note of the URI. So I'm just going to copy the URI again to my clipboard. And the command that you need to run in order to do the Docker build is docker build -t. And then just paste in that URI, okay, and followed by a space and a full stop and enter. And that's going to start the build process using the commands in the Docker file. Okay, so now it's actually running the second command, which is the install for the MySQL and PHP extensions for MySQL. So it's just going through that at the moment. Running the third command. Okay, now it's doing the copying of the source code to the HTML directory of that image. It's exporting the image and is exporting the layers, and that's done. So that has created the Docker image. If I clear the screen very quickly, and if I type in Docker images, there's our container image. There's our Docker image. Okay, it's the latest. There's the image ID. It was created 15 seconds ago, and it's 651 MB in size. Fantastic. You have now built your Docker image. In the next step, I'm going to show you how to push this image into the ECR repository. So let's do that next. Okay, so step 4 is where we're going to push the Docker image into ECR. And so we've built a Docker image with the Docker file, and now all we need to do is push that image into ECR, into the repository we created earlier. So let's do that next in the AWS Management Console. Okay, so in order to push this image into ECR, you need a set of commands. Now, if you actually go to the container registry where you created your image, if you actually click on your repository name, you will see there's obviously nothing in there at the moment. So we're going to click on View Push Commands. So this gives you quick access to the commands that you need to run. Now, for the purposes of this exercise, you're only going to need to run commands 1 and 4 because we've already built the actual Docker image and we've tagged it because we use the same URI. So all you need to do now is first retrieve an authentication token and authenticate your Docker client with the registry. So we'll do that first. So copy that command, go back into your session manager and paste that command in there, and then enter on that. And you'll see that login has been succeeded. You do get a warning message. You can ignore that for now, but you get a login succeeded, which is what you want. And the reason why login was successful was because of that IAM role we created earlier. The next command that you want to run is the actual push command. Okay, and we're going to copy this command. And because we had actually named our image exactly this way, it's just as easy as a copy and paste job. So let's just go ahead into Session Manager and we'll paste in this command. So this is the Docker push command to push that image. And that's what's happening now. The image is getting pushed from this Linux server into our ECR repository, from where we can deploy our containers. So this will take a few seconds, depending on your internet bandwidth. Okay, and that's your image pushed up into ECR. So if you now go back to the ECR registry, come out of there for a second and do a quick refresh. There's our image over there, latest. Okay, that's the actual URI, and that is our image all ready to go. Okay, so we've got our image in our repository, and so now we can move on to the next step. So next is step 5, which is our RDS database. This is where you will set up a MySQL database that will host all of the data that's collected from that front-end form on the Richer Roast web application. And ultimately, in order to set up a database, an RDS database, you do need to have a VPC. So we have that in place already. And as we've already designated the data subnets that will host our database instances. Now, one of the things that you need to do when setting up a database is you need to set up something called a database subnet group. Essentially what it is, it's a group that specifies the subnets that are going to be used to host your database. And within there, we'll deploy our MySQL database. Now, as per the previous diagram, we would also be deploying a standby instance. So we'll have a master instance and a standby instance, and then configure multi-AZ. And that's what you would do in the real world scenario. Because this is just a lab mini project environment, I don't want you to incur unnecessary cost. And so what we're going to do is we're just going to set up a single database instance. That's going to be the main database instance, and it's not going to be configured for multi-AZ. But in the real world, you really ought to be configuring this for multi-AZ to ensure high availability and failover ability for your database architecture. Okay, let's jump on into the AWS Management Console. We've got a couple of things to do. We've got to create a database subnet group, and then we've got to launch our database. Okay, so let's go into the RDS Management Console. So let's just open that up in another tab. I'm just going to shift that over here. And we'll start off by creating our subnet groups for our database. So currently there are no subnet groups. So all you need to do is click Create a DB subnet group. You'll need to give it a name. I'm going to call this one Ritual Roast DB subnet group. Okay, and self-explanatory, so we just use the same in our description. You need to make sure you select the right VPC. So obviously this is our Richer Roast VPC, and then you need to configure which subnets you're going to work with. So we're using availability zones 1A and 1B, and within those availability zones we're using the data subnet groups. Now, I know for a fact that my database subnet groups are on 10.0.21.0 and 10.0.20.0, but you can cross-reference it. So just go all the way back to your VPC console and look at your subnets. And let's just order that a little bit. So you can see that the data subnet is 10.0.21.0, and the other data subnet, the data subnet 1, is 10.0.20.0. So that's how you cross-reference it. Okay, so you know you're selecting the right subnets for your database. Okay, scroll all the way down and click Create. And that's your subnet group created, plain and simple. Okay, so now that we've got our subnet group created, we can go ahead and create our database. So from the left-hand menu, click on Databases. And then you want to click on Create Database. Click Standard Create, and we're creating a MySQL database. Okay. Under templates, you want to select the free tier because we want to create a free tier database. And so what happens is the options for multi-AZ, etc. are all grayed out because we're using free tier. For the database identifier, we need to give it a name. I'm going to call this Ritual Roast DB. Okay. And when it comes to the credentials, now we will be using Secrets Manager in order to manage our database credentials and rotate our database credentials every 7 days or 30 days, whatever your corporate policy is. But I want to leave that for a separate step. So we'll look at Secrets Manager in the next step. For now, just go ahead and choose a master username, leave it at admin, and choose a password of your choice. Make it as complex as you can. Oops, I think I typed in the wrong password there. Yep, there you go. And then we'll come back to Secrets Manager again. For the instance type and class, leave it at dbt3 micro, that's fine. Storage, 20 gigs is enough. Turn off auto scaling, we don't need that for this database. When it comes to connectivity, select the option that says don't connect to an EC2 compute resource because our application will connect to it. We're using ECS anyway. And then you want to make sure that the virtual private cloud, you select the right one. So select the Richer Roast VPC. And in there, once you select the Richer Roast VPC, you'll see that your DB subnet group that you created moments ago is automatically selected for you. So that's good. If you happen to have more than one subnet groups for your databases, obviously it will be in the drop-down list. Public access, set it to no. This database is sitting in the private subnet, doesn't need public IP. And then security group, remember we had created a security group for our database in the VPC section of this training. So get rid of default and select the RR Data SG security group. Under availability zones, we're just launching a single instance. Let's just put it in US East 1A. Check to make sure that your database port is set to 3306. It normally is. Scroll down to advanced configuration, and for the database name, use the same name, just call it Richer Roast DB. You can leave backup to 1 day, and you can leave the other settings like encryption and log exports and maintenance at their default values. Scroll all the way to the bottom and click Create Database. Now, databases take about 5 to 7 minutes to create, so this is going to take a little short while. Why don't you grab yourself a cup of coffee, tea or something. I'm going to pause the video for now and then we'll come back and continue where we left off. Okay, so here we are. Our database is up and running. It's available. It's running the MySQL engine. It's DBT3 Micro. And if we click on the actual database, we can see some information. So that's our endpoint. So the endpoint is what you'll connect to, and we'll configure all of that later when your application needs to talk to the database. It's in US East 1A. It's in the right VPC, it's in the right subnets, it's using the right security group. Great, we're good to go. So that's the database created. The next step is we're going to now configure Secrets Manager so that we can actually get the credentials of the database managed by Secrets Manager, and we can implement rotation of those credentials. And the best thing about this is that it allows you to secure your database even further. Now, the other reason why we're using Secrets Manager is because we want our applications to dynamically retrieve the current database credentials and access the database using those temporary credentials, rather than embedding the actual database credentials hard-coded in the application code, which is really a big no-no practice. You really don't want to be doing that. So Secrets Manager enables you to dynamically retrieve database credential details or private keys or API keys, any kind of secret information in a more secure manner rather than having it hard-coded somewhere. So let's move on to the next step. Okay, so let's move on to step 6, which is where we're going to configure Secrets Manager. Now, the reason for keeping this separate from the database setup, which we did earlier, was because I wanted to highlight some key configuration concepts so that you're able to apply this to real-world scenarios. So let's take a look at how Secrets Manager works. So when you deploy Secrets Manager in this architecture, the purpose of it is to basically ensure that access to the databases is done as securely as possible. Your application needs to authenticate itself against the database, and either you could hard code the database credentials within the application, which would be a really unacceptable thing to do, or you could use something like Secrets Manager, which stores the secrets, the credentials securely, and then you dynamically retrieve them when you need them. So the idea behind Secrets Manager is that it would basically be configured to host the database credentials, and that way we can dynamically retrieve them when we need them. Now, the way how this works is essentially you create Secrets Manager, you point it to the database, and you specify the credentials. There's an additional feature of Secrets Manager, which means that it's a lot more powerful than something like Parameter Store, Systems Manager Parameter Store, for this particular use case, and that is it has the ability to automatically rotate your database credentials for you. And it does this by using a Lambda function. So when you configure rotation for Secrets Manager, it actually invokes a CloudFormation template in the background, and that builds out a Lambda function that then takes the responsibility of rotating those secrets at regular intervals. So you may set the rotation schedule for every 7 days, 30 days, 3 months, whatever your corporate policy is, whatever you consider best practice for your organization. And then at those intervals, the Lambda function will kick in. It will update the database credentials, and it will also update Secrets Manager with that information. So this Lambda function needs to talk to both the database and Secrets Manager. And by rotating the secrets at regular intervals, you enhance the security of your overall architecture that much more further. Now, there's a little bit of a configuration issue that you need to take into account here. When we build out this VPC, obviously we built out these security groups, right? So for example, traffic coming out from the internet goes to the application load balancer on port 80. The app security group has been configured in such a way so that traffic from the load balancer goes to the app security group, and the data security group has also been configured in such a way so that it will only accept traffic on port 3306 from the app security group. Now, in order for this Lambda function to talk to the database, it needs to be associated with a security group that gives it permissions to do so, okay? Because at the moment, all that's happening is the databases are connected to this data security group, and they will only listen for traffic from any resource associated with the app security group on port 3306. So when we go to deploy our ECS containers and make them associated with the app security groups, those containers and the applications that run on them will be able to talk to our database. But when CloudFormation deploys this Lambda function, it's not aware of this app security group. What it actually does is it associates the Lambda function with the same security group that the database is associated with. In essence, it says, right, this Lambda function needs to talk to this database. Let's associate it with the data security group in anticipation that you have allowed traffic from the database security group to talk to itself. Do you see what I mean? So let's take a look at this in the console and it might make more sense. Okay, so here we are in our VPC. If I scroll down to security groups, let's just take a look at what's happening. So if we look at the data security group, which is already selected over there, let me just bring this in a little bit closer, just so that you can see all the columns. And what you will note is that the source of this traffic, this inbound rule, which allows traffic on port 3306, is from a security group called RR-AppSG. Okay, so currently, the only entities that can talk to our database are entities associated with RR-AppSG. Now, CloudFormation, as I mentioned earlier, isn't aware of this security group, and it will associate the Lambda function with the data security group. It will actually say, right, the Lambda function is associated with the data security group. So, go back to the slides. When the Lambda function tries to talk to the database to update the credentials, it's going to fail. Okay, so there's multiple ways of doing this. You can either create a brand new security group and then associate the Lambda function post deployment with that brand new security group, or for the purposes of this lab, you can just do something very simple. Let's go back to the VPC console. We can edit the inbound rules. Okay, I can add another rule and we can keep it to the same MySQL Aurora. And this time we can just set the source from itself. Okay, so that's data security group. Okay, let me just show you that again. If I scroll all the way down, I'm just selecting the RR data security group. Because the Lambda function will be associated with this security group anyway, right? Now it's going to be able to talk to our database. Okay, so that's one configuration change you do need to make as you're deploying this architecture. Obviously, like I said earlier, best practice would be, okay, you could also create a brand new security group, call it the Lambda security group, and then set it up that way and get the Lambda security group talking to the data security group. Back to our slides then. Here we are, back to our slides. So at this point, once you've configured the data security group with that additional rule, then our Lambda function can talk to the database and update the database credentials. There's another concept that I want to quickly place in front of you over here. This is obviously a lab environment, so we've got some flexibility. In real world scenarios, you want to consider about how traffic flows from entities in your VPC with other resources that are outside of your VPC. One of the key reasons for putting a NAT gateway is because that's the only way the traffic will flow. Okay, so this Lambda function, when it needs to talk to the secrets manager and say, hey, I've updated the credentials for my database, here they are, it needs a way to send that traffic to Secrets Manager. It's going to actually make use of this NAT gateway to get out onto the internet and then to go to the public space in AWS to talk to Secrets Manager. In a real world use case and for production environments, you probably want to think about setting up private VPC endpoints. Now, private VPC endpoints allow you to access resources in the public domain of AWS and outside of your VPC, but in a manner that uses connectivity over AWS's private networks. Okay, so it doesn't traverse the internet in any way. If you're interested in knowing how to set that up for real world scenarios, then do check out that link shown below. Okay, that link is going to give you a little bit more insight into how to set up VPC endpoints. I do want to include that in this particular video purely because as it is, this video is quite extended anyway, but it's really easy to set up. And if you want to set up a VPC endpoint, then you can follow the instructions there. As it stands, we're now ready to get into the AWS Management Console and configure our Secrets Manager. So let's go ahead and do that. Okay, so here we are back in our AWS Management Console. So what we want to do is go into Secrets Manager next. So I'm going to open Secrets Manager in a different tab. Let's bring that all the way here. And you need to click on Store a New Secret. We're creating credentials for an RDS database, so that's the right one selected. You need to put in your database username and password, so I'll just put that in there now. And then you want to select the Richer Roast DB that we set up earlier. Click Next, and then we need to give this secret a name. So I'm going to call this one Richer Roast DB Secret. Okay, and you can put in some hyphens in there so that we can distinguish it better. You can put in some description and then click Next. Now we want to enable automatic rotation. That's where CloudFormation is going to go in and create that Lambda function for us. And we're going to set it up as a scheduled expression builder. We're just going to use days and we're going to set it to 7 days. Next, we're going to go ahead and ensure that create a rotation function is enabled, and you want to give the Lambda function itself a name. So this is going to be called Secrets Manager Ritual Roast Secret Rotation. Okay, so spell that correctly. So that hopefully gives it a self-explanatory name, so we know exactly what it is, and then we click Next. Here's a review page. So we're creating it for an RDS database. That's the name of the secret. That is the automatic schedule for every 7 days. The Lambda function that's going to be created, it's going to be called Richer Roast Secret Rotation. And then you're going to click on Store. Now when you click on Store, what's going to happen is AWS will create the secret. So there it is. Okay, and it says you've successfully stored the secret, Richer Roast DB Secret. Also, it tells you that AWS CloudFormation is setting up the rotation resources. This can take up to 2 minutes to complete. So if we actually go into the secret configuration there, this is the details. So that's the name of the secret. That's the ARN. You're going to be needing those later on. If we click on some rotation, you will see that currently rotation status is disabled. That's because CloudFormation is busy setting that up, so that will become enabled shortly. So I'm going to pause the video over here because this is going to take a couple of minutes to set up. So as soon as it's enabled, I'll resume the video again. Okay, so we are back in our AWS Management Console in the Secrets Manager secret configuration page, and you can see that rotation status has been set to enabled. So just to show you exactly what happened, let's also go into CloudFormation very quickly. I'll open that up in a different tab and let's just take a look, see. Okay, so as you can see, so CloudFormation went ahead and created our RDS Secrets Manager secret rotation, and for that it created a Lambda function as well. Okay, so Lambda permissions, etc. All of that is created. If we actually go into Lambda as well, so let's just take a look at Lambda very quickly, open that up in another tab, you will see that there is in fact a function that was created. Okay, and if we go into this function, it's a Secrets Manager Richer Roast Secret Rotation, the name that we gave it, that function. Okay, so that function was created. Very quickly, I want to show you the configuration and go down to VPCs. And you will see exactly what CloudFormation has done, right? So CloudFormation placed this Lambda function in my VPC in the subnets that belong to my databases, okay? And it also associated the function with the database SG. This is why we had to configure our database SG so that it would allow traffic to any entity attached to that security group, in this case, the Lambda function, to the database. So now the Lambda function can talk to the database on port 3306. Okay, so you can see why we had to make that slight adjustment in our security group in order to facilitate CloudFormation's task that it was performing in the backend. Okay, so what I'm going to do now is just come out of this very quickly, and let's come out of this as well. We're back to our secrets. Let's move on to the next step. We've got our secrets manager in place. We've got our database in place. The VPC is all up and running. You've also got ECR with our repository that contains the Docker image. So we're really getting much further ahead than when we started. Now, as part of the architecture, you do need to distribute traffic across multiple ECS instances that you plan to deploy. In the real world use case, you would need to cater for high availability. And that means you'll be needing to think about things like elastic load balancers. So we will be creating an elastic load balancer, specifically an application load balancer that will sit at the edge of our network, allow inbound traffic from the end users, and distribute that through to our containers. As a prerequisite for creating an elastic load balancer, as a prerequisite for creating an application load balancer, you need to create something called a target group. A target group is just basically a container to host your targets. In this case, there will be the ENI interfaces, the IP addresses that point to our containers. Okay, and we need to configure our target group to accept traffic on port 80, and that target group will be the group that the load balancer sends traffic towards. So let's jump back into the AWS Management Console and create our target group first. Okay, so here we are in our AWS Management Console, and what I'm going to do is I'm going to go to the EC2 dashboard very quickly. And on the left-hand side, you want to scroll down to where it says Load Balancing and click on Target Groups. Okay, and then on the right-hand side, click Create a Target Group. And ECS Fargate requires you to configure IP addresses as your targets rather than instances. So if you're deploying EC2 instances, you would use instances, but because we're using Fargate, you want to set up IP addresses as your targets. So make sure you select that. Next, you need to give it a target group name. So I'm going to call this one Ritual Roast TG for target group. The protocol needs to be HTTP on port 80. The IP address type is IPv4. Make sure you select the right subnet. So we want the Ritual Roast subnet. We're going to stick with the HTTP1 protocol. Further down, you want to look at the health checks section. Now, this application code has got the index.html file, but it also has a health check file that is being used to monitor the availability of the website. Okay, so you just want to make sure that you type in where it says health check path, health.html. Essentially, there's a file called health.html that performs all of the health checks, or is used to perform all of the health checks. And as long as this file is accessible and responding, the load balancer will mark your services as healthy. Okay, so just make sure you enable that. Next, you want to click on Advanced Health Check Settings. Now, this is where you set up various parameters, right? Like healthy threshold, unhealthy threshold, the number of consecutive health check failures required before considering a target as unhealthy. That's set to a default value of 2. You can reduce this down to 3 if you want. Set your different timeout intervals just so that you reduce the time taken to perform the health checks. I'm going to bring this down to 10. Okay. Just bring it down to 10, that should be fine. And then that's pretty much it. Your success code is 200, so we're good there. That's exactly what we want. And then you want to go across and click next. So the targets, well, the targets are going to be in the Ritual Roast VPC. And you just want to remove that as well. It will set up all of the IP addressing for you anyway. Okay, then we go down to review targets. Now, currently there are no targets because obviously we haven't set up our containers yet. So we'll obviously be setting up that later. We'll be referencing this particular target group when we're setting up our containers. So you can leave this empty as it is and pretty much go across to create target group. So when you create target group, Currently, there will be no targets. Therefore, there will be 0 healthy targets and 0 unhealthy targets. And that's fine. It's just doing its monitoring. It's going to be looking out for this health check file. It can't see any instances or any targets at the moment. Therefore, it will not respond with any healthy or unhealthy targets. That will come later on once we put ECS in place, once we set up the load balancer, and once we reference this target group from our ECS configuration. Okay, so that's your target group setup. Let's move on to the next step. Okay, with the target group created, we can go ahead and create our application load balancer, which is step 8. So now that we've got our target group created, all we need to do is deploy the application load balancer. Now the application load balancer needs to be configured in such a way so that it sends traffic to the target group. The target group will contain the targets, a pointer to our containers. Let's jump back into the AWS Management Console and configure the application load balancer. Okay, so back to our AWS Management Console, what you want to do is go down in your EC2 Management Console to Load Balancers, and you want to click on Create a New Load Balancer, and the one that you're creating is an application load balancer. So let's hit Create on that. We'll need to give the load balancer a name. So I'll call this one Ritual Roast ALB for application load balancer. It's going to be an internet-facing load balancer because it's going to take traffic from the web and distribute it to our containers, IP address IPv4. For the network mapping, make sure you select the right VPC, and then you want to choose the availability zones where you have your subnets in. Now, the load balancer is going to deploy load balancer nodes in the public subnets. Okay, so you want to make sure you select the public subnets, which is that one over there, and yep, that one over there. Okay, so the 2 public subnets across the 2 ACs. For the security group, remember we created this in the VPC section of this training. Go down to and select the ALB security group. That's for the application load balancer, configured to accept inbound traffic on port 80 from the internet. And so when it accepts the inbound traffic on port 80 on the internet, you want to send that traffic to the target group we created moments ago. So that's the Ritual Roast target group. So there it is. Okay, and then if you scroll further down, pretty much that's all the configuration you need in the real world. For production applications, you may want to integrate with the web application firewall as well as the global accelerator depending on your use case. So just look at the review. So that's the Ritual Roast ALB, internet facing, associated it with the ALB security group in the right subnets, sending traffic to the right target group, and we're pretty much good to go. Go ahead and click Create Load Balancer. It takes a little while for the load balancer to come up, probably a minute or so. Okay, so after a few seconds, if we hit the refresh button, there you go, it's set to active. Okay, so that is now up and running. Our load balancer is running just fine. And actually there's a new feature here. So if you click on resource map, you can actually see the overview of how the traffic flows. So traffic from port 80 gets forwarded to the target group, which is the Ritual Roast TG. Obviously there are no targets at the moment, so we can't see the entire resource map. Okay, right, let's move on to the next step. Now I know what you're thinking. How many steps does this project actually have? We're getting there. Trust me, we're getting there. Okay, so step 9 is all about IAM roles and policies for your ECS tasks. So essentially, we've got our VPC in place, we've got our subnets, we've got our database, we've got the security group sorted out. We also have the load balancer, ECR with the Docker image, and even Secrets Manager done. You're doing really well. So the next step is we're going to set up some IAM roles. Okay, in fact, we're just going to set up one IAM roles, but with a couple of IAM policies. So the situation is this. Your ECS containers that you deploy within your VPC are going to need to be able to do a couple of things. They're going to have to be able to download that image. Okay, you'll be creating a task definition that will specify what the image is, which is this Ritual Roast image over here. So it needs permission to download that image. It also needs to be able to send log information to CloudWatch and a couple of other things. In addition to that, the containers, the application, needs to be able to reference the secrets in Secrets Manager in order to talk to your database. So those containers are going to need permission for that purpose as well. And that's where the IAM role is going to come in. You're going to create an IAM role so that you can grant permissions to retrieve secret from Secrets Manager and to be able to communicate with ECR and send log information to CloudWatch and stuff like that. Let's do that next in the AWS Management Console. Okay, so here we are back in the AWS Management Console. So for this particular task, you want to go into the IAM dashboard. So I'll just open that up in another tab as well. And the first thing we want to do is create a policy for Secrets Manager. Okay, then we'll create an IAM role that will be attached to that policy. So on the left hand side, go down to policies, click create a policy. This is a customer managed policy as opposed to an AWS managed policy, because you have to manage this, you're creating this. And you can use this visual representation. We can go down to Secrets Manager. Okay, so just see Secrets Manager, there we are. And then you want to search for, in terms of the actions, there's a get secrets action. So there it is, get secret value action. That's the one we want. And then when it comes to the resources, you really should be specific about the resource you want to interact with. So you could set it to all, or you could click on specific. And if you're clicking on specific, you need to add the Amazon resource name of the secret. So let's grab hold of the Amazon name of the secret that we created. So if I go back to my Secrets Manager, you'll see there's the secret ARN. This is for the Richard Rose DB secret. So I'll quickly copy that to the clipboard. And then I can add ARN. And for the resource ARN, we'll just paste that in there. Okay, so that picks up the fact that it's in the US East 1 region. That's the resource secret, and then that's the ARN. So we'll click add ARNs, and you can even view the JSON thing there. So you can see what it is. It's going to allow Secrets Manager get secret value specifically for that secret ARN. Okay, so we're good there. So we can go ahead and basically click next. And then what you want to do is provide a policy name for this policy. Okay. Ritual roast allow read DB secret. Okay, something like that. CCRET policy. Okay, so that's very clear exactly what it is. You can put it in the description if you want. You can see what it's doing. It's going to allow access to Secrets Manager, specifically the read access. And then we click create policy, and that's our policy created. So if I do ritual roast up there and just filter on that, you'll see there it is over there, ritual roast. Okay, so that's our policy created. Great, fantastic. Okay, so the next step is let's go ahead and create an IAM role. Now remember, this IAM role is going to have two policies attached to it. One is this secret policy that we just created, and also another policy in order to interact with ECR and with CloudWatch. So from the left hand side, we'll click on create a role, and the role you're creating for is an AWS service. The use case is for the Elastic Container Service. So if I just search for that here, Elastic Container Service, that's the one there. Okay, and specifically you want it for the Elastic Container Service task. Okay, so that's what we're looking for. So we're going to go ahead and click next on that. And then we're going to attach a policy. Now we're going to attach an AWS managed policy. So AWS has already created a policy that you can use, and that's the Amazon ECS task execution role policy. Okay, so that one over there. And if you expand that, you'll see what it does. So it allows ECR access as well as sending logs to CloudWatch. Okay, so we need that. And then obviously in addition to that, we also need to provide access to the policy we just created. So let me just cancel there and do ritual. There it is. Ritual roast allow read DB secret policy. We want that one as well. So we've ticked both of those. So if we click next, you'll see the two permissions are going to be added to this IAM role. The Amazon ECS task execution role policy and the ritual roast allow read DB secret policy. Exactly what we're looking for. And then we just need to give it a name. So I'm going to call this one ritual roast ECS task role. Okay. and then scroll all the way down and click create role. So that's my role created, Richard Rose ECS task role. Okay, it's got the necessary policies in place. We can now proceed with the next step. Okay, step 10 is where we're going to go ahead and create an ECS cluster. Now, an ECS cluster is essentially a logical grouping of all of your containers, whether that's the Fargate collection or whether that is the EC2 launch type collection of containers. And essentially, you need to create this cluster in order to define the infrastructure that you're going to work with, within which you're going to define or set up your containers. So you'll need to define whether it's going to be a Fargate launch type or an EC2 launch type. Right, let's jump into the AWS Management Console and set up our ECS cluster. Okay, so here we are on our AWS Management Console. And so what we need to do is just go to the ECS service. So Elastic Container Service, I'll open that up in another tab. And I don't have any clusters at the moment, so just go ahead and click Create Cluster. And then you need to give your cluster a name. So I'm going to call this one Ritual Roast ECS Cluster. Okay, and there you go, and that's the name. And then this is where you define the infrastructure. So if you were doing our containers based on EC2 instances where we manage the containers, then you have all these other parameters to configure. But seeing as we're just going with the Fargate service, it's fairly simple. That's the serverless service, and essentially that is where AWS will manage the underlying instances that will manage your cluster for you. And the Fargate cluster takes away a lot of that overhead with regards to the administration part of your cluster. Okay, so this is what we're going to do. And then all you need to do is click create, and that's your cluster getting created. Okay, so that's the Richard Roast ECS cluster created. We can move on now to the next step. Okay, so here we are, step 11. Okay, we're almost there. In this step, we're going to go ahead and create the ECS task definition. So the ECS task definition requires several parameters that you will provide in order to build out your containers. You'll deploy the ECS task definition and provide various configuration pieces of information. For example, you provide information on the AWS Secrets Manager that you will be using in order to obtain those credentials for the database. You'll also define necessary IAM roles, and you will configure certain environmental variables. In fact, one of the environmental variables will be the name of the secret that is in Secrets Manager. So your task definition is where you basically bring all of the core components together. You define exactly how your containers are going to be built out. And obviously in the task definition, you're also going to include which Docker image, which container image to use. In this case, our Richard Roast image, which we created a bit earlier in this mini project. So let's go ahead, let's jump back into the AWS Management Console and configure a task definition. Okay, so here we are back in our Elastic Container Service. We've already built the cluster. So the next step that we need to do is build out a task definition. So if you click on task definition on the left-hand side and then click create a new task definition, we'll need to provide a name for our task definition family. Okay, something like that. And then the launch type is where you want to make sure you select AWS Fargate. Now the underlying host operating system is going to be Linux, okay? And because you're selecting Fargate, the network mode is already set for you at AWS VPC. You then need to specify the task size. So how much CPU and memory you want to allocate to your tasks. This task or the application is fairly light, so we can go with something like 0.5 vCPUs, and perhaps let's just select 1 gig of memory. That should be more than enough. Previously, we'd created the IAM role, so you need to select that IAM role we created, which was the Richard Roast ECS task role for your task role, as well as for your execution role. Okay, so these have the permissions to allow container agents to make API calls on your behalf. And the task role is going to use the permission allocated in the role to access Secrets Manager. Okay, so we've got that bit set up as well. Okay, so next we're going to provide container details. This is where you specify the name of the container and the container image you're going to be using. So we're going to select Ritual Roast here and the image URI. So this is the URI of the actual Docker image you're going to be using. So if we go back to the Elastic Container Registry, This is the URI over here. So we're just going to go ahead and copy that to the clipboard and then go back to our location and then just paste it in there. Okay. And we'll mark it as an essential container. Next, you need to define port mappings. So for that, we're selecting port 80, the TCP protocol, and we're going to be going to the HTTP app protocol. So that's exactly how it should be. Next, if you scroll down towards environmental variables, now this is where you define the environmental variables that your task definition, your tasks will use in order to interact with other services. So specifically, for instance, the database service and of course, Secrets Manager. So let's provide those environmental variables. So the first one is the DB server. So just type in DB server exactly as is shown on the screen. So in capital letters, it's a value, and you need to provide the endpoint of your database. So if we go back to our RDS console and click on databases and then click on our Richard Rose database, this is the endpoint address. So just copy that to your clipboard, back to the task definition, and that's the value we're putting in. Okay, so that's your database server, that's the RDS endpoint. Next, another environmental variable. This time it's going to be the DB database. Okay, just make sure you obviously spell that out correctly, otherwise it's just not going to work. So that's the name of your database, and you would recall that the name of your database is just Richard Rose DB. Okay, so you want to just copy that portion of it. It's just Richard Rose DB. And let's just plug that value in there, and that's the actual database name. Next, we need to provide the secret name. So secret underscore name. So that's the way how you want to spell it out. Secret underscore name, again, all capital letters. Value, and provide the name of your secrets. So if we go to the secrets management console, the name of our secret is just here. Okay, Richard Rose -db secret. So we'll plug that value in there as well. And then finally, you need to specify the region. So you want to go AWS underscore region. And the region we're operating in is obviously the US East 1 region. Okay, and that's where all of our workloads are going to be placed, in the North Virginia region. Next, if you scroll down, you've got logging, which is optional. Leave these values as it is, at their default values. That's going to send some log information to CloudWatch basically, and you can review that at a later stage to analyze what's happening in your environment. Finally, scroll all the way down, leave everything else as it is, and we don't need to add any storage or anything, and click create. So that's going to create your task definition for you. Okay, and that's your task definition created successfully. Right. So if we look at your task definition, you can see your task size, it's set to those parameters, the name of your container, the image it's going to use. And at present, we're obviously not specifying any task placement strategies. That's a bit of an advanced topic, but obviously it's something that you probably want to read up on for real world use cases for production environments. Okay, so your task definition is all good. Let's move on to the final step. Okay, welcome to step 12. This is where we actually go and create our ECS service, which will deploy those containers into our cluster, and we should then be able to access our application. So let's see what happens. We've got the task definition. We're going to now build out a service. That service will allow us to specify how many tasks to deploy, what the autoscaling policy is, and all those finer details, which will then trigger the deployment of our tasks. When that happens, containers will be deployed in our Fargate cluster, and ENIs will be injected into our VPC, through which we can access our containers. Users on the internet then can access our service, the Richard Rose application, via our load balancer, which will send traffic to our ECS containers. Right, let's jump on into the AWS console and quickly set this up. Okay, here we are back on our AWS Management Console. So we're currently looking at our task definition. If I go back to the cluster and click on the cluster, you will see that I've got a services tab over here. This is what we're going to use. Click create to create our service. And obviously you want to make sure that you select launch type, and you want to make sure that that is set to Fargate using the latest platform version. Scroll a bit further down And this time we're not deploying a single task, we're deploying a service, because that allows you to define all of those additional parameters with regards to scaling and stuff like that. And they're ideal for long running compute workloads that can be stopped and restarted. Whereas the task one is just for things like batch jobs or standalone tasks. Okay, so next you want to go down to the task definition and click on family and make sure you select the task definition that we defined earlier. We're using the latest revision, so you can have multiple revisions obviously, but we just want to use the latest one. And then we want to go and provide a name for our service. And I'm going to call this one Ritual Roast Service. Okay, so Ritual Roast Service is the name of our service. Okay, and then you want to select the service type. That should be set to replica anyway. Now, in terms of desired tasks, we're just going to go with the one desired task. We are obviously testing this out in just a lab environment, but in the real world, you'll think about how many tasks you need to deploy. You've got deployment options over here. Leave these at their default values. Basically, this refers to how you want to perform your updates, whether you want to do a rolling update, in which case you specify your minimum number of running tasks and maximum number of running tasks during an update process, or a blue-green deployment. Next, let's scroll further down, and what you want to do is expand networking. Now in the networking, make sure you select your VPC, that's the Ritual Roast VPC, and specifically you want to make sure here that you select just the app subnets. So we want to get rid of that public subnet, that data subnet, we want that one, the app subnet, we don't need this data subnet, we don't need this public subnet. So you should have remaining just the app subnets, which is where your containers are going to be deployed. You then need to define a security group, not the default security group. Obviously, we want to allocate these containers to our app security group because that has the right set of inbound rules. We do not need public IP for our containers. They are, after all, in the private subnet, so that's good. Next, load balancing. So you expand this tab, and yes, we do want to use a load balancer, an application load balancer, and in fact we want to use an existing load balancer that we've created already. So from this drop down box, select your load balancer, and then next you want to define the listener. Now we already have a listener, so just select use an existing listener and use this listener that we have set up earlier. This is where you define the target group. Here again, remember we had already set up a target group. So use an existing target group and select the Ritual Roast target group. It's got the health check part set to /health.html. That's exactly how it should look. Okay, so next we want to go with service autoscaling. Now with service autoscaling, this is where you define how you scale out your tasks and scale back in using a particular scaling policy. So enable this service autoscaling box, and what you want to do is set the minimum number of tasks to 1 and the maximum task to a particular value, let's say 4 for instance. In terms of the scaling policy type, so just select target tracking, that's fine. And then we just need to give it a policy name. So I'm going to call this one Ritual Roast Auto Scale ECS, okay, something like that, that to do it. And the service metric that we're going to be using is CPU utilization. So what we're saying here is that if the utilization of my task goes at a target value of 70, then we want to make sure that we scale out, and you can allocate a particular scale cooldown period and a scale in cooldown period as well. So a scale out to cooldown period and a scale in cooldown period. Okay, so this is the configuration for the service autoscaling. Remember, this is scaling out your containers, not the instances that host your containers. We're not using the EC2 launch type, so we don't need to worry about that. We're using Fargate, which means AWS takes care of the instance autoscaling. Okay, so scroll down a bit further, and then all we need to do is click create. I'm just going to run through very quickly and make sure that all the settings are fine. Launch type Fargate, latest platform service. That's our task definition. Yep, replica, that looks good. With regards to the networking, we're in the right VPC, we're using the right subnets. We're using an existing group called the app security group. No public IP. We're using our existing load balancer, existing listener, existing target group, and then we've enabled service autoscaling as well. All looks good to me. Go ahead and click create. Okay, now this is what's happening in the background. The service is being deployed. Okay, the task, the Ritual Roast service deployment is in progress. Takes a few minutes, so we'll wait a few minutes. I'm going to pause the video over here and come back as soon as it's all up and running. Okay, welcome back. So as you can see, my Ritual Roast service has been deployed successfully, It's in the active status. There's a default monitoring going on. And if you look under services, there's my Richard service up and running. It's got 1 of 1 tasks running. That's exactly what we wanted to see. Okay. And that all looks very good. In fact, if we go to tasks, you can actually see the task as well. So this is the task ID. It's in the running status. And we've got the task definition that it's using. I know it says health check unknown there, but actually the health check, remember, is also being performed by the load balancer. So if I go back to my load balancers and click on target group and click on Richard Rose target group, you'll see that I've got 1 healthy instance or 1 healthy container running there. Click down here, you can see the actual IP address of the container, and there it is in the healthy state. So that's fantastic. If we go back up to the load balancer, okay, and just bring this up a little bit, actually just click on the load balancer. Okay, there is the DNS name of my load balancer. So the moment of truth, guys, let me just copy that to the clipboard and paste that in there, enter, well, voila. There is the Richard Rose website. It's a beautiful website, even if I do say so myself. Not much of a front-end developer myself, but there you go. Okay, so that's the Richard Rose website. And we've got okay, what have we got here? Some images, logo, some more images, next month's beverage, public poll. So this is where Richard Rose would like to engage with their customers, with members of the public, to try and see if they can get them to provide some feedback as to what drink they would like to see as the next month's beverage. So we can put in our name. Let's fill up this form whilst we do it. I'm going to put in a name. So let's call myself John and give myself an email address, john@example.com. Okay. And choose a drink. I quite fancy gingerbread latte, and hit submit. And it says, thanks for voting. That's nice. Might want to change that dialog box, but that's okay. Click OK again. And if we scroll further down, look at that. Look at that. I've got a list of current voters. So I admit I did test this out before. I wanted to make sure this all works, and it did work. So I'm just testing it out again. But let's put in another name, shall we? Let's go with Alice. Alice at example.com. And let Alice choose vanilla spice latte and hit submit. And it says, thank you for your vote. And look at that. We've got 2 votes for gingerbread latte, 1 for vanilla spice latte. So if you guys go ahead and vote on this, then hopefully we'll know what's coming next month for our beverage of the month. A very simple website, folks. Don't want to complicate this part of it, but I wanted to illustrate various elements that go to build a multi-tier architecture. You've got the front end, you've got the back end with the database, you've got security with the Secrets Manager and all of the, well, security at all layers really. You've got security at the network layer, at the application layer, IAM roles, etc. And obviously we've got a fully functioning web application that's running as a container, that's running on ECS Fargate, which is an absolute joy to build. Well, I hope you really enjoyed this mini project, folks. I hope you go out there and actually try out all of the various exercises and the components of building out this end-to-end solution. Remember, you've got access to all of our application code, as well as all of the necessary pieces of information in this video to go out and build this yourself. The more you play with the AWS platform, the more you create and build solutions, the more confident you're going to get. And that's going to make you even better as a solutions architect or a developer or a cloud engineer, whatever your current role is, or whatever role you're hoping to work towards. Okay, so please do practice on the AWS platform. Now, technology is always improving. You know, what is available today is going to be old news tomorrow. And the folks at AWS, Docker, Kubernetes may have even further, more innovative ideas for containerization. Interestingly, I came across a video that they may actually find useful in getting some bright ideas for further innovating containerization. Want to check it out?
Now, repositioning empty containers is a massive headache for the shipping industry as it's expensive and time-consuming. Korea has developed a solution, foldable containers, that could save the industry a lot of money and a lot of hassle. Park Se-young has the details.
This shipping container folds to a quarter of its original size in less than 10 minutes. It was developed by the state-run Korea Railroad Research Institute to reduce the cost of shipping and storing empty containers. Not only is it one of the first of its kind, Korea's Transport Ministry says it's the most efficient and reliable folding container to be developed in the world so far.